Okay, so for the second half of this section, 2.3, I believe, we are looking at rational functions. So a rational function is just a function where we have a ratio, which where rational comes from, a ratio of polynomial functions. And so we usually write this f of x equals p of x over q of x. P of x is a polynomial, q of x is a polynomial. And this function will be defined wherever q of x is not 0. And so wherever it is 0, you either have what's called a hole in the graph, which most of the time we don't have that in this course, or we have what's called a vertical asymptote. So here you see y equals 1 over x. So we have the polynomial 1, the constant polynomial 1. We have the linear polynomial x on the bottom, 1 on the top. And so this gives us, these are called vertical asymptote, or a vertical asymptote. As we get closer to 0 in this case, on this side we're going down to negative infinity. As we get closer to 0 on this side, we're going up to positive infinity. And by closer to 0, I'm talking about the x, as x gets closer to 0. And then we also have horizontal asymptotes. Now, we may or may not have those. Most rational functions have vertical. Most of them have horizontal. Most of them have both, probably. But we'll talk about how we can find those horizontal asymptotes as we go out, as x goes out to infinity, what's happening with the function. So in this case, imagine plugging in bigger and bigger numbers for x. And what happens? You end up with 1 over a big number. And so that will go to 0. And so it never actually approaches 0, or it never actually equals 0. It approaches 0. And we can see it happens the same way in the negative direction. So what else do we have? We have, so asymptotes, here is the definition. So if a function gets larger and larger in magnitude without bound as x approaches the number k, so whatever 0 in the last example, then the line x equals k is a vertical asymptote. And you can have those anywhere. We could have one that comes like that. So if this was at 3, then 3 would be a vertical asymptote. And you could have it go in opposite directions like in the last one, or the same direction. So in this case, they're both going down. And so with any asymptote, as you get past a certain point, and with a vertical asymptote, the graph will never cross a vertical asymptote, but it will get closer and closer. So as you go down, keep going down to negative infinity in this case, or as x gets closer to 3 in this case, I should say, then the graph will go towards negative infinity. And so that number will get smaller or bigger and bigger on the negative end. Then in the other way, if the values of y approach the number k as the absolute value of x gets larger, so you could say as x goes to positive infinity or as x goes to negative infinity, then the line y equals k is a horizontal asymptote. So if we called this, say, 4, and let's draw an imaginary line here, this one, and let's say this gets closer and closer. So x is going out to negative infinity out here. X is getting bigger and bigger and bigger in the negative direction, and y is getting closer and closer to 4. It will never actually get to 4, but it gets close to 4. And you could have functions where, if you have a horizontal asymptote here, and it could cross it somewhere up here. It could cross it again. It could cross it however many times you want, but eventually it's not going to cross it. It's going to get closer and closer. I don't know that we'll see too many of those in this class, but that is a possibility because there's nothing wrong with this. But eventually it gets closer to that line and never cross it again. It'll just get closer and closer. With the vertical asymptote, you can probably imagine you can't cross a vertical asymptote, because if you crossed it and then came back, now you're failing the vertical line test. And so that doesn't work. So a vertical asymptote, you're not going to cross it. So how do we find these? So finding asymptotes, these are very simple. It's just very simple rules to follow. So to find the vertical asymptotes, factor the denominator completely, set the denominator equal to 0, and then solve for x. Any of those x values are possible vertical asymptotes. If a factor cancels, it creates a whole. So an example of this would be f of x equals x squared minus 9 over x plus 3. And so if we factored the numerator here, we get x plus 3, x minus 3 over x plus 3. The x plus 3's cancel. And so this is essentially, this function is equivalent to this function, f of x equals x minus 3, with the only point being x equal to negative 3, because negative 3 makes this denominator 0. So x cannot equal negative 3. So what this graph looks like is this linear function, slope of 1, y-intercept of negative 3. But when x gets to negative 3, you have a hole in the graph. And so otherwise, it's just a straight line. Again, I don't know if we'll see many of those in this class, but something to keep in the back of your mind. When you factor the polynomials in a rational function, if anything cancels, the cancellation will create a hole at whatever would make that 0. Most of the time, you're going to have pretty simple, let's say 1 over x plus 4. So this would have a vertical asymptote at x equals negative 4, because that would make the bottom 0. So whatever that graph looks like at negative 4, you're going to have a vertical asymptote. Okay, now the horizontal asymptote doesn't really require math like the vertical. It's more rules to remember. So compare the degree, which is the highest exponent, we mentioned that in the last video, of the numerator and the denominator. So if we have, let's say, g of x equals x squared plus 2x minus 2 over x cubed minus 5. So here's a rational function. We have the degree in the numerator is 2, the degree in the denominator is 3. So we're comparing these two. So in this case, the numerator degree is less than the denominator degree. So the horizontal asymptote will be at y equals 0. So what that means is this function in particular, as x gets bigger and bigger, and either in positive direction or negative direction, it doesn't matter. This one, we'll just say g goes to 0. So as x gets really big, so, however big you want to make it, 10 to the 1000th power, something. This ratio gets closer and closer to 0. And the reason is because when you cube a big number, it's much bigger than when you square that same number. And then these two don't really matter, and the 5 doesn't matter once x gets really big. If the numerator degree equals the denominator degree, the horizontal asymptote is the ratio of leading coefficients. So let's look at this one. Let's say h of x equals 2x squared minus 5x, and then the bottom is 3x squared minus 2, we'll say. So here we have a degree 2 on top, degree 2 on the bottom. So now it's the ratio of the leading coefficient. So the ratio of 2/3. So here we have a horizontal asymptote of y equals 2/3. And I guess we should say here we have a horizontal asymptote of y equals 0. Then last, if the numerator degree is greater than the denominator degree, then there is no horizontal asymptote. So let's look at this example. F of x is, say, 4x to the 5th minus 9x squared plus 7, or whatever else we have. And then let's put this x squared minus 2. So here we have the degree on top is 5, the degree on bottom is 2. So in this case, as x gets larger and larger, x to the 5th, or a big number raised to the 5th power, is going to be much, much larger than a big number squared. And so here, no horizontal asymptote, because this is just going to go off to infinity, as if you look at the graph. And again, when we're looking at these horizontal asymptotes, and we're going to look at limits in the next chapter, that's where we start to get into the calculus things. And this is kind of thinking about limits without calling it limits. When we talk about x getting really, really big, 9x squared and 7 and 2 are not affecting 4x to the fifth. And even x squared is not affecting 4x to the fifth once x gets really large. So when x gets really large, either positive or negative, you really only have to worry about whatever the largest exponent in the function is. Okay, so let's look at graphing these, and we're going to kind of employ the same strategy that we saw in the polynomial video. We don't need to precisely know how to graph this. What we do need is to figure out where the differences are in these choices that we're given. So again, I copied this straight from the MyMathLab homework. And so let's look at the asymptotes. So that's the best place to start. So you can see this one has a vertical asymptote around 1 and -1, probably. This one has a vertical asymptote at 1, and then these two don't have a vertical asymptote. So they're both continuous. So to find the vertical asymptote, we set the denominator equal to 0, and wherever x is, that will tell us where the vertical asymptote is. So there's no way to factor these to cancel anything out, so we don't have to worry about holes. Now, notice this, so if we can move the x or the 1 over, we get x squared equals -1. So there's no solution to this. So no solution means no vertical asymptote. So that tells us it's not this one and it's not this one. So now, what's the main difference in these two? Well, the horizontal asymptote, but also notice the y-intercept for these. The y-intercept is negative here and positive here. So if we could find the y-intercept, plug x equals 0, and what do we get? Then we get y equals -3. So that tells us that it's going to be this one. So easy enough. Now, the other way, possibly you could have it to where the y-intercepts are the same or close enough to the same that you can't really tell which one is which. So the other way that the other information that we can get that's helpful is to find the horizontal asymptote. So here we have the let's call it the numerator degree. The degree on top is 2, and then the denominator degree is also 2. So these are equal, and that comes up to this one. So the horizontal asymptote is the ratio of the leading coefficients. So the leading coefficient is -4 and 1. So this tells us that the horizontal asymptote, -4 over 1, or just -4. And so we can see here's your horizontal asymptote. I guess we put that under here. And so that's this one's obviously not -4. This one must be -4. So there you go. So between these three things, and if possibly you could have x-intercepts. None of these have x-intercepts, but that's another piece of information that could be helpful. But between these three things, that's probably going to be enough when you're just looking at multiple choice answers, which the homework is just going to be multiple choice, and the test as well. So, all right, here's another one. So let's consider again the vertical asymptotes. So x minus 4, set the denominator equal to 0, we get x equals 4. So here we have that probably is at -4, so that one doesn't work. Here we have a vertical asymptote at 0, that doesn't work. And then it looks like these two are probably at x equals 4. So it could be either one of these two. All right, so what else do we have? If we plug in, so find the y-intercept. So plug in 0, and we just end up with -1/4. So 0 plus 1 over 0 minus 4, that's -1/4. It's pretty hard to tell, and you could zoom in these in on MyMathLab, and you might be able to tell, but too close to call, I think, on either of those. So that's not very helpful in this case. Horizontal asymptote, the numerator degree is 1, the denominator degree is 1, so we're looking at the ratio of the coefficients, which are both 1, so y equals 1. And it looks like this one has a horizontal asymptote that's negative. This one has one that's positive, so it's going to be that one. All right. So that's that, and I went through the homework just to kind of make sure you didn't have to do anything too different from this. there may be some definition questions and other things, but as far as the graphing part, this is really all you need. They're multiple choice, and so you just kind of you don't need to be able to draw it by hand. That's not really what we're interested in. We're interested in can you find characteristics of a graph to help you figure out what it looks like, and that's what we'll be doing a lot of as we go along. So if you have any questions, let me know.